Hello everyone. Now in this lecture we have started our next unit, that is third unit, Combinatorics. And in this new unit, Combinatorics, in this lecture we are going to study a point, that is counting. And in this lecture we are discussing about what is the counting, what are the different types of the counting, and what are the basics of the counting. Now let's see here the introduction part of the counting. Combinatorics is the study of the arrangements of objects, and it is an important part of the discrete mathematics. Enumeration is the counting of objects with a certain properties, and it is an important part of the combinatorics. So the counting, it is used to solve many different types of the problems. For instance, counting is used to determine the complexity of the algorithms. Complexity is also required to determine whether there are enough telephone numbers or the internet protocol addresses to meet the demand. So these counting techniques are also used extensively when the probabilities of the events are computed. So this is all about the introduction part of the combinatorics and the counting. So combinatorics is nothing but the arrangement of the objects, and counting is used to solve many different types of the problems. And counting is also used to mind the complexity of the algorithms, and probabilities of the events are computed by using the counting. Now let's see here the basics of the counting. Suppose that a password on a computer system consists of the 6, 7 or the 8 characters, and each of these characters must be a digit or a letter of the alphabet. So each password must contain at least one digit. So the question is here, how many such passwords are there? Means by using this computer system consists of the 6, 7 or 8 characters. So each of these characters must be a digit or a letter of the alphabet. And so by using this, how many such passwords are there, or how many such passwords we can create? So this is a problem. So how we can solve this problem? Okay, so at that time the combinatorics is useful, that is counting is useful and this in this situation. So counting problems, such type of the counting problems arise throughout the mathematics and the computer science. For example, to count the number of the operations used by an algorithm to find its time complexity. Okay, so to solve such type of the problems, we can use the counting, the basics of the counting. Now let's see here, what are the different basic counting principles? There are the two basic counting principles. First one is the product rule and second is the sum rule. Now let's see these points, or let's see these basic counting principles one by one. These principles are used to solve many different counting problems. These methods serve as the foundation for almost all the counting techniques. So see here, these principles are very useful because these act as the foundation for the almost all the counting techniques. So the product rule applies when a procedure is made up of the separate tasks. When we can apply this product rule? When a procedure is made up of a separate tasks. Now what is the product rule? Now what is the definition of the product rule? Suppose that a procedure can be broken down into a sequence of the two tasks. Okay. Then if there are n1 ways to do the first tasks and For each of these ways of doing the first task, then there are n2 ways to do the second task. Then there are n1, n2, n2 ways to do the procedure. Okay, this is the product rule. What does it says? A procedure is broken down into a sequence of the two tasks. Okay, so if there are n1 ways to do the first task, means first task is completed into the n1 ways. Then for each of these ways of doing the first task, there are n2 ways to do the second task, right? Because if the first task is completed by using the n1 ways, then obviously the second task can be completed by using the n2 ways, because the procedure is broken down into the two tasks. First task is completed into n1 ways, and second task is completed by using the n2 ways. Then what is how we can conclude this statement or principle or product rule? Then there are n1 multiply n2 ways to do the procedure. Okay, so this whole procedure or whole task can be completed using the n1 multiply n2 ways. So this is our product rule. Okay, so this is the description about the product rule. Now let's see some examples of this product rule. First example, the question is a new company with just two employees. Two employees are there named Prem and Nitin. These two employees rents a floor of a building with 12 offices. How many, now the question is that how many ways are there to assign the different offices to these two employees? Okay, what is the question? A new company with just two employees, Prem and Nitin. That these two employees rents a floor of a building with 12 offices. Means there are the 12 offices are there and employees are only two. So question is here, how many ways are there to assign the different offices to these two employees? Now see here the solution. The procedure of, now to solve this problem we are using the product rule. Okay, the procedure of assigning the offices to these two employees consists of assigning an office to Prem, which can be done in 12 ways. Simple. Means the procedure of assigning the offices to these two employees consists of assigning an office to first employee. The first employee is that Prem. So to Prem we can assign the office in the 12 ways. How many ways we can assign the office to the Prem? In by using the 12 ways we can assign an office to first employee, that is Prem. Then assigning an office to Nitin different from the office assigned to Prem, which can be done in 11 ways. Okay, why 11 ways? Because 12 ways are assigned to first employee, which is Prem. That's why from that ways, remaining ways are assigned to the next employee, which is Nitin. So by using the 11 ways, that offices are assigned to the second employee, which is Nitin. So by the product rule, there are 12 into 11. 12 ways are used by the Prem, assigning the offices to the Prem, and 11 ways, different ways are assigned, assigning an office to second employee, which is Nitin. So 12 into 11 is equal to the 132 ways to assign the offices to these two employees. Understood? The question is that 12 offices are there and how many ways we can assign these offices to the two employees. 12 are offices assigned to the first employee, which is Prem, and remaining ways, which are 11 ways. 11 offices are remaining, which can be applied to the Nitin. That's why By using the product rule, 12 into 11 is equal to 132 ways are used to assign the offices to these two employees. Let's see another example. The question is that the chairs of an auditorium are to be labeled with a letter and a positive integer not exceeding 100. The question is that what is the largest number of the chairs that can be labeled differently? Okay, let's see here again the question. The chairs of an auditorium are to be labeled with a letter, means letter are used to label the chairs. Also, a positive integer not exceeding 100 means the chairs of an auditorium are labeled by using a letter and a number also. And the question is here, what is the largest number of chairs that can be labeled differently? The question is here that means we have to find out that what is the largest number of the chair that can be labeled differently. Okay. See here the solution. The procedure of labeling a chair consists of the two tasks. Which are those? First one is assigning one of the 26 letters, because in the question it is given that our chairs are labeled by using the letters. So how many letters are there? Alphabets 26, A, B, C, D up to Z. So assigning one of the letters 26 letters. Then assigning one of the 100 possible integers to the seat, means chairs. So the question is that positive integer not exceeding 100 and the letter. By using this letter and number, we are labeling the chairs of an auditorium. So there are the two tasks are there. One is 26 letter and another is 100 possible integers not exceeding 100. So by using the product rule, it shows that or it states that there are 26 into 100 means 2600 different ways that a chair can be labeled. So by using this statement or by this statement says that the largest number of the chairs that can be labeled differently is obviously 2600, that is 2600. Understood? Means there are the two tasks are there. One is 26 letters and another is 100 possible numbers which are not greater than 100. So by using the product rule we can multiply these two numbers 26 and 100. So the answer is 2600 and this is our largest number of the chair. Next, let's see here another example. How many different beat strings of the length 7 are there? The question is what? Beat strings of the length 7 means we have to find out the string whose length is the 7 and how many such beat strings are there of length 7. Each of the CS solution, each of the 7 bits can be chosen in two ways. Okay, so as you already know that each bit is either 0 or 1. Therefore, the product rule shows that there are a total of 2 raised to 7 is equal to 128 different bit strings of length 7. So the question is here, how many different bit strings of length 7 are there? So each of the 7 bits are chosen in the two ways. What are these two ways? Either 0 or 1. So by using this 0 or 1, we can show that product rule. By using the product rule, there are total of 2 raised to 7. Means we want the bit string of length 7. That's why by using the bit 0, there are the 7 ways, and by using the bit 1 there are the 7 ways. So 7 length of the bit string is of length 7. That's why 2 raised to 7 is equal to the 128 different bit strings of length 7. Next, how many different license plates are available if each plate contains a sequence of 3 letters followed by the 3 digits, and the no sequences of letters are prohibited. The question is, what is the question, or what we want to find out? How many different license plates are available if each plate contains a sequence of the 3 letters followed by the 3 digits? So there are 26 choices for each of the 3 letters and the 10 choices for the each of the 3 digits. Why there are the 26 choices? Because we have the letters available from A to Z is 26, and the 10 choices. 10 choices means 0 to 9. There are the 10 choices for each of the 3 digits. So hence, by the product rule, there are total of 26 into 26 into 26 into 10 into 10 into 10 is equal to 17 1,75 1 crore 75 lakh 776,000, means 17,576,000 possible license plates are there. How so much numbers are there to make a license plates, different license plates? So how we can get this answer? Because by using the product rule, there are the two tasks are there. First, by using the letters, 26 letters, and again by using the digits, 3 digits. That's why we are by using the product rule, multiplying 26 3 times and 10 numbers or 10 digits 3 times, we get the result. These many possible license plates we can made available. Next, another rule is the sum rule. If a task can be done either in one of n1 ways or in one of n2 ways, where none of the set of n1 ways is the same as any of the set of n2 ways, then there are n1 plus n2 ways to do the task. This is our sum rule. So previous PPT we have seen the product rule. Now this is our sum rule. What does it says? If a task can be done either in one of n1 ways or in one of the n2 ways, but condition is what? Where none of the set of n1 ways is the same as any of the set of n2 ways. If this condition is satisfied, then and then only there are n1 plus n2 ways to do the tasks. So to understand this sum rule, let's see some examples. The first example, suppose that either a member of the mathematics faculty or a student who is a mathematics major is chosen as a representative to a university committee. So how many different choices are there for this representative if there are 37 members of the mathematics faculty and 83 mathematics majors, and no one is both a faculty member and a student? So this is our question. Now let's see once again what is the question. Suppose that either a member of the mathematics faculty or a student who is mathematics major is chosen as a representative, means we want a representative which is either mathematics faculty or a mathematics student. So the question is that how many different choices are there for this representative if there are 37 members of the mathematics faculty, means there are the 37 faculty members, and how many students are there? 83 mathematics students are there. The condition is what? No one is both a faculty member and a student, means no one is both faculty and student also. So now let's see here solution. There are 37 ways to choose a member of the mathematics faculty, and there are 83 ways to choose a student who is a mathematics major. Now, choosing a member of the mathematics faculty is never the same as choosing a student who is a mathematics major, because our condition is there, no one is both a faculty member and a student. That's why by using the sum rule, it shows that, or it follows that, there are 37 plus 83 is equal to 120 possible ways to pick this representative. Understood? Means there are also two different ways, 37 ways for the faculty, 83 ways for the student, and no one is both the faculty and a student also. That's why by using the sum rule we can say that 37 plus 83 is equal to 120 possible ways to pick our representative. Next, a student can choose a computer project from one of the three lists. The three lists contain 23, 15 and 19 possible projects respectively, and no project is on more than one list. So how many different possible projects are there to choose from? Again read this question. A student can choose a computer project from one of the three lists. Means there are the three lists are available, and a student must have to choose from these three lists. What are these three lists? Three lists contains 23, 15 and 19. And the condition is what? No project is on more than one list. Means these three lists are different. No two lists contain the same project. Okay. All these three lists are different projects. The question is that how many possible projects are there to choose from? The solution: the student can choose a project by selecting a project from the first list. Okay, student can choose a project by from the first list also, can second list also, or the third list, because no project is on more than one list. So means each project contains the different projects. No two list contains the same project. So by using the sum rule we can say that there are 23 different plus 15 which are also different plus 19, these are also different. Means by adding these three ways we get the answer 57 ways to choose a project. Okay, next let's see here the pigeonhole principle. Now see here what is the pigeonhole principle, and by using this, or by using the introduction part we can see what is the pigeonhole principle. Suppose that a flock of the 20 pigeons are there which are flying into a set of the 19 pigeonholes to roost. Roost means what? Roost means a branch of the tree upon which a bird can rest at night. Okay, a branch upon which a bird can rest at night, that is called as a roost. So there are the flock of the 20 pigeons flies into a set of the 19 pigeonholes. Because there are the 20 pigeons, but only 19 pigeonholes are there. Means pigeons are more, but pigeonholes are less than the pigeons. So at least one of these 19 pigeonholes must have at least two pigeons in it. So to solve this problem, we have to contain at least one pigeonhole must have at least two pigeons in it. Okay, then and then only this problem can be solved. If each pigeonhole had at most one pigeon in it, then at most 19 pigeons, one per hole, could be accommodated. Okay, means in each pigeonhole at most one pigeon in it, then at most 19 pigeons one per hole can be applied. So this illustrates a general principle, and that principle is called as a pigeonhole principle. And this principle states that if there are more pigeons than pigeonholes, then there must be at least one pigeonhole with at least two pigeons in it. Okay, what does it say? There must be at least one pigeonhole with at least two pigeons in it. Similarly, we can say that this principle can be applied to the other objects besides the pigeons and the pigeonholes. Now, by using this principle, there is one theorem of this pigeonhole principle. If k is a positive integer and k plus 1 or the more objects are placed into the k boxes, then there is at least one box containing the two or more of the objects. Now see here again, if k is a positive integer and k plus 1 or more objects are placed into the k boxes, then there is at least one box containing the two or more of the objects, and then only this principle can be satisfied. Okay, so in this lecture we have seen the our new chapter or new unit, that is combinatorics, and in that we have now we have discussed about the counting and introduction about the counting, its basics of the counting, the product rule and the sum rule, and our next principle, which is the pigeonhole principle. Okay, thank you.